When we calculate the amount of emissions that we get from burning some combustible, it's usual to give the amount of CO2 that we are emitting. But an important question is that when we burn, we not just get CO2, but we can get other molecules that can have sometimes a larger impact than just CO2. In this video, we are going to we will learn how to get an average number that is giving me the amount of warming potential that we get from some combustion due to the combination of all the molecules that we get in a combustion. Okay, we start by analyzing the data of carbon dioxide getting from Mauna Loa Observatory. This is the widely known data that is the evidence of the increase of carbon dioxide. But an important thing here to see is that the amount of carbon dioxide that we emit increases mostly during the winter, because we are heating our houses, we are using much fossil fuels. But at the spring, the nature is reabsorbing all part of this carbon dioxide because of the natural growing of the vegetal life. So sometimes it's increasing, sometimes it's decreasing, but at the end, the net amount of carbon dioxide is increasing because what is being removed during the spring cannot be as large as the amount of carbon dioxide that we emit during the winter. The important fact here is that the amount of CO2 can be reabsorbed in the earth because of this absorption due to the trees and the vegetables in general. In this plot, we can see how is this decay of the molecule that we are emitting in terms of time. So how do we expect that our emissions evolve? So if we emit an amount of carbon dioxide in 1 year, if we let the time pass, this amount of carbon dioxide is going to be reabsorbed some part in the oceans and in the vegetals, and at the end it will be decaying. Another important question is the warming potential of the different molecules that we emit. That is, how efficient is the molecule in producing the greenhouse effect. And in fact, carbon dioxide is not so efficient at this. If carbon dioxide has a potential of 1, methane has a potential that is 80 times larger. So it means that this molecule is much efficient at warming the earth than this. So the question is, why this molecule is much famous than this when we talk about climate change? The reason is that it's because the persistence of methane in the atmosphere is lower than the persistence of CO2. Here we can see the same level of the amount of methane that we emit in terms of time, how much of this methane is persisting in the atmosphere, and we see that in 40 years almost all the methane that we have emitted has been reabsorbed in the earth, while the CO2 still remains there. When we analyze the radiative forcing, that is, how much greenhouse effect is creating carbon dioxide, methane, and the rest of the molecules, we see that because carbon dioxide it has a very large persistence, its effect is so high, and methane it has a very large effect. not because of its persistence, but because its potential of warming. So remember, it has a very large warming potential, while CO2 has a very large persistence. So this means that these molecules has a high effect because of its persistence, and this has a high effect because of its warming potential. So these two effects can give the different molecules different importance in the radiative forcing of the Earth. To obtain the different importance of the two molecules with time, a thing that we can do is this CO2, CH4, is to making averages in different amounts of time. So, for example, let's take at 20 years, we can obtain an average value so analyzing the area of this plot of CH4 with the area of CO2 and multiply the warming potential by the fraction of this value. If we do it, for example, at 100 years, you will see that in this case methane will be completely absorbed, and that at the end you will have CO2. This allows us to calculate the average warming potential at different years. And if we compare methane with carbon dioxide, we have said that methane is 80 times more powerful in warming potential than carbon dioxide, but because this difference in persistence at 20 years is like saying that it's 72 times larger than carbon dioxide. And if we do it at 100 years, due to the large persistence of CO2 and the lower persistence of CH4, it's like CH4 has a warming potential of 25, only 25. Look that there are other molecules that it has a very high warming potential, so like 300 or almost 23,000 times than of CO2. But these molecules are not so important. If we come back to the table, are not so important because the amount of these molecules that we are emitting is very reduced compared to the amount of methane and the amount of carbon dioxide. And at the end, these two are the most important. So if we want to know the warming potential that an amount of emissions can have, we have to calculate it all with a single value. And the standard way to do it is to calculate the amount of carbon dioxide that is equivalent to all these emissions. And let's do it. Okay, 1 kilogram of CO2 is obviously 1 kilogram of CO2. But 20 grams of CH4 at 100 years, due to the power is 25 times larger, it's like 0.5 kilograms of CO2. Multiplying 25 by 20 grams is 500 grams, that is half a kilogram of CO2. This means that 20 grams of methane, it has a warming potential equivalent to half a kilogram of carbon dioxide. And 1 gram of nitrous oxide, it has a warming potential 298 times larger. It means that 0.298 kilograms of CO2. If we add all these values, it means that this level of emissions with this combination of molecules, it has the same warming potential as 1,398 grams of CO2.